All right. So welcome to Unit 6 lecture of CE305, which is Languages and Compiler, or as I like to call it, the module on how to build your own compiler. You will find the lecture notes available on Moodle under Unit 6. Just give me 1 second to see if it's recording. Yeah, it is recording. All right, quick recap. But before we go into recap, can someone tell me what is the job of the parser in the chat? So in your answer, mention what is the input of a parser and what is the output of the parser. Okay. Anyone on the chat? What is the job of the parser? So what the parser takes that as input and what does it output? Can you put that on chat, please? So Stefan has mentioned takes input like integer number and transform it into tokens. No, not correct, Stefan. That's the job of a lexer or a lexical analyzer. So parser does parsing. What does parser takes as input and what does it output? Andre mentioned parser creates tree. Yes, that is correct. Partially, that is correct. Sokanya has mentioned the parser creates a hierarchical tree. That is correct. Curtis has mentioned, I think the job of the parser is to take in the tokens from the lexer, groups them, and creates an abstract syntax tree. Yes, that is correct. So Andre mentioned by using tokens. So as some of you have already mentioned it correctly, the parser takes in the input of tokens from the lexer and outputs either the parse tree or abstract syntax tree, which is also a form of intermediate representation, right? Now, let's dive into today's lecture. So, a parser is technically a compiler or an interpreter's component that takes input in the form of sequence of tokens, interactive commands, or program instructions, and breaks them up into the part that can be used by the components in programming. Now, that's the general definition. But because we are mostly working with compiler, or we are learning about compiler, in compiler, the parser takes in the token and then it outputs as either parse tree, which is also called concrete syntax tree, or it outputs as abstract syntax tree. And these are also the form of intermediate representation code, which will be further used by the components of the compiler for further processing. So parser takes an input string and it will tell whether that input string is in accordance with the grammar production rule or not, which means it will either accept the string or it will reject with certain error. Now, parser can be of two types. One is top-down parsing and other one is bottom-up parsing. We will be going into details for top-down parsing and bottom-up parsing shortly. But if you can recall from previous lecture, Top-down parsing is more about expansion of the rules, production rules, whereas bottom-up parsing can be thought more as compression of the rules to reach the final production rule. Okay, so first we are going to look into top-down parsing itself. Top-down parsing is a parsing strategy where one first looks at the highest level of the parse tree and works down the parse tree by using the rewriting rules of the formal grammar. So let's take a look into the definitive steps that you need to take as part of performing top-down parsing. First construct the top node of the tree, and then rest of the node in pre-order or depth first approach. Pick a production rule and try to match that input. If you fail any moment, then you backtrack. Essentially, using these steps, we try to find a leftmost derivation for the input string, which we can scan from left to the right. Now, some grammars are backtrack free, for example, predictive parsing. So right now, if you are a bit confused, we will see with examples that how to perform top-down parsing. Now, as I've mentioned, that some top-down parsing mechanism, which is like recursive descent, or as I've mentioned here, so predictive parsing, right? It's a form of recursive descent top-down parsing. So recursive descent is a top-down parsing technique that constructs the parse tree from the top, and the input is read from left to right. It uses procedures for every terminal and non-terminal entity. So let's take a look into the steps in order to perform recursive descent top-down parsing. So construct the root with the start symbol of the grammar, and then repeat until the fringe of the parse tree matches the input string. Assuming a node labeled A, select a production with the A on the left-hand side, and for each symbol on its right-hand side, construct the appropriate child. So when a terminal symbol is added to the fringe, find the next node to be expanded. So we looked into the theory of how to perform the top-down parsing, right? Let's dive into an example. Let's say if you have a grammar with these production rules, where you have the root production rule as goal produces EXPR. EXPR produces EXPR plus term, or EXPR minus term, or term, and so on. So these are the production rules that are provided as part of the grammar, right? Now, using this grammar example, let's perform the top-down parsing. So you start from the goal, which is the root production rule, and then you expand it. How you do it? So as it's mentioned here, goal produces EXPR. We do that. We choose goal produces EXPR. Now EXPR can produce several other, let's say, production rules, right? But we choose EXPR minus term. So if we choose that, then EXPR is expanded to EXPR minus then term. And then the first EXPR here on the left-hand side, we expand that. So one of the, based on the production rule provided, we can choose any of these, but we have chosen for this particular example to go for the EXPR that can expand or produce term, factor, and X. So we are choosing this one where we have the term. So EXPR can be term, produces the term produces the factor. So using that, we have expanded the EXPR like this. On the right-hand side of the operator minus, you can see now we have term that needs to be expanded, and we expand again the term on the left-hand side. And we continue doing this till we have created the parse tree. Now, this is the practical way of performing a top-down parsing, but it has its own shortcoming. One of the thing that you might have noticed already, that if you choose the wrong production rule, that can lead to non-termination. For example, using this production rule, what if instead of choosing EXPR produces term and term produces factor, we have chosen EXPR plus term, and we keep on expanding that? You will see it will never end in that way. So the parsing doesn't reach the end. And that is a problem or shortcoming for this kind of top-down parsing. So when that happens, that the choices you make to choose the production rule that leads to non-termination, that is a very bad property for a parser. So for a parser, the desirable is that it must make the right choices so that it can terminate at some point. Now, that being said, so far, do you have any question? All good, everyone on the chat? Okay, thank you, Curtis, for confirming. Okay, so a grammar is left recursive if it has a non-terminal symbol capital A such that there is a derivation where capital A produces capital A alpha or capital beta. So here, capital A is a non-terminal and alpha and beta are tokens. So given this theory behind left recursive, what we can say that it can also indirectly produce the production rule, which forms of capital A produces capital B alpha or capital C. Capital B produces capital A beta or capital D. So here capital A, B, C, D, these are all non-terminals. So note from here that a left recursive grammar can cause a recursive descent parser to go in an infinite loop. Because if we extend the non-terminal to another non-terminal and we continue like that, and it doesn't reach a terminal, then if you can try to put that mentally, an image, how the production rule is going to expand, you can see if we use these two production rule in that way, non-terminal leading to non-terminal, it will continue doing that. So we have to reach a point where it ends with a terminal instead. But if we use this where non-terminal leads to non-terminal, then it goes into an infinite loop. So let's consider another example. It's the same one from the previous one where capital A produces capital A, alpha or beta. Now here we can remove the left recursion in the following ways, right? The way we approach it is actually by converting the left recursion to right recursion. And how we can achieve that is that, let's say, given this production rule, which is the production rule for, let's say, the left recursion, where capital A, which is a non-terminal, produces capital A, alpha, or beta, we create a new production rule where we call it capital A dash produces alpha followed by capital A dash or epsilon. And as you all know that epsilon is an empty string in the production rule in grammar, right? So by introducing this production rule, which is actually right recursion, we can now reach a terminal using the main production rule, which is this one. So the way we do it is that, let's say we start with capital A, that now we have, we replace the capital A dash with alpha A dash. And then we use the production rule again from here and start replacing the capital A dash and replace it with alpha A dash or epsilon. By the way, we have someone put something in the chat. So Andre has mentioned A produces AAB looks like magic for me. What these variables mean? Andre, these are not variables. These are production rule, right? Now, if you can recall that in our labs, when we formed the grammar, you have a similar type of notation, right? You have non-terminals produces non-terminal or non-terminal produces terminal, right? So this is where you are saying that A arrow, A alpha or beta, right? This is a type of a production rule. So visit previous week's lecture and we actually talk about this, like what is a production rule and how to like form these production rule. So you will get a bit better understanding. But for now, imagine that a grammar consists of rules, right? And we call them production rules. The way you denote production rules is in this manner. What is shown here on the screen, right? So what it means, as I've already mentioned, the capital A is technically a non-terminal that produces, again, capital A, alpha. Now, alpha here is a terminal, or beta. Beta is also a terminal. So Curtis has asked, not too sure if this is a dumb question, but is there any instance where left recursion will not produce an infinite loop? Yes, there is an instance, Curtis. So let's say for left recursion, if instead of having a production here for the left recursion, where it doesn't have capital A alpha, instead it's just alpha, which means that non-terminal produces a terminal. If a left recursion consists of such a production rule, then you do not have to worry about going into infinite loop, because there is nothing to expand and you have already reached a terminal, right? But the example that we are working on here, because capital A here on the left can be expanded with using this production rule, so we can replace the capital A with capital A alpha slash beta again, right? And we keep on doing that. In that way, capital A will be always replaced by capital A, and it will continue doing that like for infinity. So for this particular production rule, it is like it's almost impossible to reach the like termination, because there is no like terminal entity. That's why we need to convert, in case if we have end up with a production rule that looks like this, then we have to convert that into another form where we can use right recursion. And the way we do that, as I have mentioned here, that we form new rules based on this production rule, where we expand A to beta A dash, and A dash produces alpha A dash or epsilon. So one solution of kind of avoiding this kind of non-termination is that you change it to right recursion. So you create new rules in order to make right recursion happen. Does that make sense, Curtis? Awesome. Great to hear. Thank you so much. Okay. By the way, another person has mentioned something. Alpha, beta, and F silent is terminal rule. Am I correct? So not terminal rule, they are terminals, right? So grammar consists of production rules. Production rule can consist of terminals and non-terminals. Now, usually on the left-hand side, you have non-terminals in the production rule, which is, let's say for here, A is a non-terminal because that produces either it can be terminal, non-terminal, or terminal, non-terminal together. For this particular production rule, sorry, let me get my mouse. For this particular production rule, left-hand side is always a non-terminal, which produces non-terminal and terminal, right? So alpha, beta, for this particular example here, alpha, beta are terminals. Now, again, Andre, do visit the previous lecture, like from last week. We specify a bit more and go in depth with the production rule in general, right? So it might make it easier to understand. Okay, thank you so much for confirming. Okay, so avoiding the left recursive rule, as we have seen already, we create new rules to be able to do right recursion instead. So there are general solutions to this by replacing left recursion with right recursion. For immediate left recursion, we replace the rules with the form like this. So realize here, right? We have the non-terminal followed by a terminal, right? Or it could be something in a similar format. So this is a left recursion. The way we do it is that if in case any of the production rule in your grammar has a form like this, replace that with a form like this, which is the right recursion instead. So the way you would do it, that you create new rule where non-terminal leads to terminal followed by non-terminal. And also make sure that the non-terminal has a way to reach epsilon, which is a completely empty string, or it can be a form of terminal followed by non-terminal itself. In this way, you do not go into the problem of infinite loop. So another thing I would also like to mention, that when you are creating new production rule for like right recursion, do avoid naive recursive descent parsing. So always make sure that you are thinking ahead while you are making the production rules. And if you just build a right recursion by like creating production rule which are naive in the sense that you do not think ahead, then you might still reach the same issue or problem as left recursion does. So do keep that in mind. Now, let's recap what we have learned so far. So we have learned the top-down parsing, which is you can do recursive with backtracking, which is not usually often used in practice. And you have the other top-down parsing, which is recursive predictive. So that is without backtracking, which is generally used in most of the like programming languages that we might cover. Now, we can also produce a top-down parser. If it picks the wrong production rule, it has to do some form of backtracking in order to choose the right one. We have also noticed that recursive predictive parsing works only on grammar where the first terminal symbol of each sub-expression provides enough information to choose which production to use. Now, how about look ahead in input and use context to pick correctly? As I've already mentioned, that do not use naive right recursion, right? So the way you do it is by looking ahead. So using the concept of look ahead to avoid this type of like any form of ambiguity or issues that might occur. Now, that being said, the biggest question here is, okay, how much look ahead is needed? So in general, an arbitrarily large number of look ahead might be needed. But fortunately, most programming languages programming language construct fall into a subclass of context-free grammar that can be parsed with a limited number of look ahead. And that being said, when we say limited number, we denote it with a variable called k. So we have the form of grammar, which is called LLK grammar, where we do left to right parsing with leftmost derivation and k number of token look ahead. So in formal languages, an LL grammar is a context-free grammar that can be parsed by using an LL parser, which parses the input from left to right and constructs a leftmost derivation of the sentence. So to resolve all potential conflicts, the parsing algorithm has to look ahead a certain number of characters, which is k number of characters. We have someone post something in chat. Okay, why not LRK? We will be discussing LRK shortly, Curtis. So be patient, we are reaching there, okay? So as you have mentioned, in LL, we do a look ahead of k number of tokens, right? So this gave rise to additional hierarchical class of grammar known as LLK grammar that recognizes a subset of context-free grammar-based languages. Now, there are all kinds of questions that can be considered here, such as whether the string of a language generated by a given LLK grammar can be recognized by like a language of LLK dash grammar, where k dash is less than k itself. So this is a kind of question which is very popular in the theoretical perspective of LLK grammars. Now, as Curtis has asked, okay, why not LRK? But we also have another technique, which is like LR. And in that, let's first take a look into what is the shortcoming of LLK. So the weakness of LLK parsing is that they must predict which production like rule to use, having seen only the first K tokens of the right hand side, right? And we call this a weakness because it doesn't have more information, or it doesn't have more information. So in comparison, a more powerful technique is LRK parsing, which is able to postpone the decision until it has seen input tokens corresponding to the entire right-hand side of the production. So in this way, on the right-hand side of the production rule, you are aware of what is going to happen. And that's why LRK is used instead of LLK. And in LRK, it stands for left to right parsing, rightmost derivation with K number of token lookaheads. Curtis, does that now make sense? That why we will use LRK instead of LLK? Okay, thank you so much for confirming, Curtis. Now, the other type of parsing is bottom-up parsing, right? So let's look into or dive into bottom-up parsing concept. So a bottom-up parser discovers and processes that the tree starting from the bottom left end and then incrementally works its way upwards and on the rightwards. So what are the steps you need to take in order to achieve bottom-up parsing? Construct the tree from an input string, beginning at the leaves and working up towards the top or the root. In bottom-up parsing, using left to right scan of the input, it tries to construct a rightmost derivation in reverse form. Now, note that this handles a large class of grammar. Now, this is a theory behind performing bottom-up parsing, but shortly we will also see with example that how you can actually achieve this. So let's take this example where you have grammar for expression analyzer, right? So the production rules form of E produces E plus T or T, and T produces T star F or F, and F produces E within bracket or ID, right? Given these production rule, if the input string consists of ID star ID, so the way you perform bottom-up parsing is that here you choose the left-hand side of the string, which is the ID, then you use the production rule which matches this ID, right? So as we have seen that F produces ID, so we replace the ID with F produces ID. And then we again take the F and we see which production rule matches with the F itself. So T produces F. This is the production rule. And we replace this F with T produces F. And from the previous one, as we already know, F produces ID, we have that as well. And we keep doing that till we have formed the total parse tree. So this is how you approach bottom-up parsing. Now, Someone posted something in the chat. Curtis has mentioned, isn't the first one left recursive, or am I reading it wrong? By the way, it is from the left hand side, but it's not left recursive because you are not expanding the production rule. Remember? So in left recursive, which is top down parsing, we start from the production rule and we reach the input string. But in bottom up parsing, we actually start from the input string. So from the other side. And from the input string, we apply the production rule to create the parse tree. So the main difference between top-down parsing or bottom-up parsing is how or where you start. For top-down parsing, we start from the production rule and we expand the production rule. Whereas in bottom-up parsing, we start from the input string and we replace parts of the input string with the production rule to form the parse tree. Okay, now one form of bottom-up parsing is shift-reduce parsing. So shift-reduce parsing is a form of bottom-up parsing in which a stack holds grammar symbol and an input buffer holds the rest of the string to be parsed. So we use the $sign to mark the bottom of the stack and also the right input. So when we want to perform shift reduce parsing, we need two things. First, the stack, which is denoted by $, and we have the input string, which we denote with the W. Initially, the stack is empty, and the input string, which we call as W, we assign the input string with to the W on the input. Now, how to do that? We will take an example and perform right reduce parsing. Okay, so remember the same example that we have used for bottom-up parsing, which is if you have the input string as ID star ID, right? So remember the input initially we denote as W. So W equals ID star ID. So the first ID, let's call it ID1, and the second ID, let's call it ID2. So that's the input string. Now we have to use the stack to kind of derive to the production rule for E, right? That's our goal. That's how you generate or create the parse tree using bottom-up shift-reduce parsing. So first, you have the input, which is ID1 star ID2. We take one of the, we start from the left-hand side. We take the terminal, which is ID1. We put that in the stack here, as it's shown. And then we reduce the ID1 by F produces ID production rule. And then we reduce the F using the production rule T produces F to the T. And we continue doing this till we have reached non-terminal. And then we shift again from the input, we now shift the operator. Now, since operator can't be reduced, so we further shift a terminal from the input as we have shown here with the ID2, and we keep reducing the terminal using different production rule, and we keep going till we reach the final production rule, which is E produces the T. And because E is part of the grammar here, which is because as you can see, E produces E, right? So this is accepted as the accept input for the shift reduce parsing. Now, so far, any question? Does this make sense that how in practical sense we can use stack and input to perform shift reduce parsing? No question? Good. Okay, thank you so much, Curtis, for confirming. Okay, so in essence, what we have noticed that the a parser, like the parser, shifts 0 or more input symbol onto the stack and until it is ready to produce a string beta of the grammar symbol on top of the stack. It then reduces the beta to the left-hand side of the appropriate production rule. The parser repeats this cycle until the stack contains the start symbol and the input is completely empty. And if that happens, then the sentence, input sentence is valid. Now we have someone post something in the chat. Andre has asked, is production rule some sort of lift up and shift is like communication on a floor? Andre, it's not really like that. So the production rule is what the defines the grammar for a particular or specific language, right? Now, using the production rule, if you have to do parsing, it can be of two forms, top down, bottom up. But the way you approach it is just slightly different. So if you are doing top down, using the production rule, you take the non-terminals from the production rule and you expand it. So when I say expand it, it means that you are replacing the non-terminal with the production rule to reach a terminal. But in comparison, in the bottom-up parsing, okay, I also would like to add the reason why we expand the non-terminals from the production rule to terminal is because when you expand, at the end, you end up achieving a parse tree in that manner. And same in bottom-up parsing, which is the other way of doing parsing. Again, remember the end goal of parsing is to generate parse tree. So the bottom-up parsing, instead of starting from the production rule to expand it, we start with the input string. And with the input string, we take, start from the leftmost side. We take the, each part of the input string, and then we replace it with the production rule. And finally, you will see you would have reached the start symbol, which is the part of the production rule, right? But when you are performing the compression, because you are starting with the input string and you are trying to replace it with different production rule to reach the start symbol, you will see again the parse tree is created in that form. Okay, I hope that makes sense, Andre. Okay, perfect. Moving along. Okay, so as I mentioned here, the parser, which is the shift reduce parser, repeats this cycle until the stack contains the start symbol and the input is completely empty. And in that sense, the input sentence is actually valid, which means it's part of the production rule and the grammar that is being defined for that particular language, which means the input string or the input sentence is part of that language. Now, this one, we have the, this is also known as LRK parser or LRK parsing. But the K here relates to the number of symbols that have to be considered when generating the table. So in bottom, now here in shift reduce bottom up parsing, right? As you can see, we are using stack and we have the input string, right? You can actually form a table where you can keep all these terminals and operators or tokens. These are all tokens from the input string. You can form a table to keep them by like replacing like all the production rule, and this whole thing, the stack and the input, can be converted to a table. So that's why we call this as LRK parsing, because here the K relates to the number of symbols that have to be considered when generating the table. Now, as with LLK definable languages, there are questions as to whether the language generated by a given LRK can be considered with LRK dash grammar, where K dash is less than K. So that's a big theoretical question that's still being asked when it comes to LRK grammar. So in case if you go into the academic route of pursuing research in this area, and if you also end up creating your own LRK grammar for the language that you are developing, so this will be one of the big questions that you might need to consider or you might want to explore. We have another for a subset of this, which we call LR1 grammar, which are widely used to construct efficient and flexible parser automatically. So here, one is literally like forms the like one symbol that needs to be considered to generate the table. Okay, now that we have looked in two different types of like parsing mechanism, let's look into ambiguity that can happen in grammar because of parsing. Now, an ambiguous grammar is a context-free grammar for which there exists a string that can have more than one leftmost derivation or parse tree, while an unambiguous grammar is a form of context-free grammar for which every valid string has a unique leftmost derivation or parse tree. We will like take a look with example actually what this means in essence. So let's take the example that you have a grammar. So this, remember in last week, we also learned EBNF form, right? Backus-Naur form, or like extended Backus-Naur form. So this is the grammar representation, EBNF representation of the grammar, where E produces E plus E, or E star E minus E, or E within brackets, or ID, right? So these are the production rule provided as part of the grammar. So if we consider that you have the input string or the input sentence like ID plus ID star ID, right? So if you are provided with the input string like this, you can actually parse it in different ways, right? So one way is this one, where you start by replacing from the left-hand side, and you replace it with the grammar production rule that is provided here. And you keep on expanding till you reach ID plus ID star ID. But if there's another way as well, so you start from, again, the production rule E, and you replace it in a different way, and you end up reaching like the same input string, the way you parse or the way you actually replace the production rule, that can vary as well. And if that happens, it can also lead to two different or multiple different types of parse tree. The example, for example, here, if the your final goal is to reach this input string, which is id plus id star id using the production rules as provided here, as you can see, for the same expansion, you can have two different types of parse tree. So in this scenario, what we need to keep in mind that we need to, as you can see, this is an ambiguity, because even if the production rule leads to the same input string or input sentence, but the way you have reached it are different. So this is an example of ambiguous grammar or ambiguity in grammar. So the way we avoid it is to definitely find a solution. And the solution in this case is to force the parser to recognize high precedence sub-expressions first. What do I mean by that? So you tell your parser, so you write the production rule in such a way that it tells the parser that you need to follow some form of precedence, which means that star has higher precedence over plus. So in your grammar, you have to make it more like known. So you have to make your grammar know this form of precedence to avoid any form of ambiguity in grammar. Now, someone has posted something in the chat. Andre has asked, is this tree mirror each other in nearly all cases? I wouldn't say it's actually a mirror, Andre, because as you can see right here, a mirror image would be, even if you invert them, they have the same operators in this at the same level of hierarchy. But here you can see they are not. So here, the like, let's say the higher precedence is the plus sign and the lower precedence is the star sign, right? But on the other tree, this one has the star or the multiplication sign has a higher precedence than the plus one. So these are not technically the mirror image of each other. But when you expand based on the production rule to reach the same input string, the biggest issue that we find is that, okay, we can come up with multiple different type of parse tree, right? But how to know which one is the correct one? In order to do that is, as a programmer, you define your grammar in such a way that you provide precedence in your grammar. So now the grammar has no ambiguity because the parser would know that, okay, this has higher precedence than the other one. And in practical, I have also told you the same thing as well during our practical with Antler. When you create the grammar file, like you create the production rule, put higher precedence production rule above the lower precedence one. Okay. Thank you so much for confirming, Andre. Okay, moving on. So with top-down parsing, a different choice of rule can generate different sentences. We could generate all possible parses by forcing backtracking even when we recognize a sentence. Now, we have got something in the chat. Okay, Curtis is asking for break. Okay, right after this, we will take a short break, Curtis, so don't worry. So The syntactic structures corresponding to all permutations of the application of rule that lead to the sentences being recognized represent all the possible parsers. So keep this in mind. Now, on the other side, with bottom-up shift-reduce parsing, different choices of reducing and shifting yield different parsers. When attempting to parse programming languages with an LRK, table-driven grammar, this is sometimes called shift-reduce conflict and reduce-reduce conflict. So ambiguity is considered to be intrinsic feature of natural languages at all levels of analysis. Parsers for natural language may be designed to be efficient at finding all possible analysis of a sentence. So as a programmer, it is your duty to keep in mind that, okay, the ambiguity can happen. And it is also your duty to be able to avoid ambiguity by providing a solution. One such solution is providing precedence as part of your production rule for the grammar. Now, with design languages such as programming languages, ambiguity is considered to be a bad thing that should definitely be avoided. Parsers for programming languages may be designed to be efficient on the assumption that the language is not ambiguous. This assumption is often relied upon in LLK or LRK parsing. Hence, shift reduce and reduce reduce conflict needs to be resolved as well. Now, what is shift reduce and reduce reduce conflict, right? So shift reduce is where the parser cannot decide whether to shift or to reduce. One example is dangling else grammar, where usually due to like ambiguity in which else to choose, you have to like, it's called a dangling else, and ambiguity occurs because of that. For we will see that shortly with example, that what is a dangling else ambiguity in grammar. But for right now, just keep in mind that the solution to resolve this is that modify the grammar in such a way that it resolves in favor of a shift, a correct shift. On the other hand, we also have reduce conflict, where the parser cannot decide which of these several reductions to make. For example, here, if the input string, you are given that ID, open bracket ID, comma ID, close bracket, right? How do you know whether this ID is actually an array or a function? So it creates ambiguity because of that, and reduction would of this input string would actually depend whether ID refers to the array or ID refers to the function. And in this case, it would be a difficult thing to tackle because you would need more information on this ID, whether to determine it's an array or function itself. Now, before we move along with example to work with shift reduce conflict and reduce conflict, let's take a 5-minute break, okay? And we will be back in and resume in 5 minutes. Let me pause the recording. Okay, it's recording again. Welcome back from the break again. So as we have noticed, like we have shift reduce conflict and reduce conflict. In general, an example of shift reduce conflict can be dangling else grammar, where you have multiple if else and your parser is not able to understand which else to parse first, right? Whereas in reduce conflict, an example can be when you have a string like ID followed by left bracket ID comma ID right bracket. Here you are not sure whether this first ID is an array or a function, right? So in that scenario, reduce conflict will be happen. So in case you do end up having ambiguity in your grammar, what can you do, right? So as I have mentioned, avoiding ambiguity is very important. The way is you need to come up with solution. One of the solution is re-expressing the grammar in a way where sometimes the grammar can be rewritten to avoid unintended ambiguity. Now, this is not always desirable as the resulting grammar can be hard to read. The other solution is that operator or rule-based precedence, where you resolve the ambiguity by imposing a precedence on the operators. This can be implemented in LRK parsing by having the table determine the next operation in those cases where a choice of operation would otherwise be available. And we have also seen with example how you can actually like provide operator or rule-based precedence to reduce any form of ambiguity. That example was this one. Here, like star should have higher precedence than the plus. So that's how you can avoid one form of ambiguity. Now, earlier I have mentioned that we have the dangling else problem, right? So what does that mean? Let's take this example. So if you have if else statement, something like this, where if B1, then if B2, then S1, then S2. As you can see, there are so many else and like then and if. So a parser might find it difficult to parse this one if the grammar isn't like defined correctly, like the production rule in the grammar are not defined correctly, because that will lead to ambiguity. Let's take this example and see how that ambiguity can happen. So let's assume that the production rule for the grammar is defined something like this. If you have if statement, so if produces if Boolean comma statement. If statement can also produce if Boolean comma statement comma else comma statement. And as you can see, like for statement, you can have like it produces simple statement, or it can produce if statement or loop statement. And loop statement produces while Boolean statement. So these are the production rule already provided as part of this grammar, right? Now, based on the example that we just noticed, and based on this grammar, if you have the input string, something like this, like if A, if B, statement A, else statement B, then using the production rule of this grammar, you will actually see the parser will be able to derive both of these like a parse tree itself. So the way it will parse, you will see both of these are valid for this particular grammar, which is definitely like causing ambiguity because it can either of these two, which is not desirable, right? So the dangling else can be resolved in this case using the precedence rule, or simply tricks the grammar to favor the first interpretation. So the way you can actually avoid this ambiguity is by rewriting the production rule of this grammar using these production rules. So what you do, you have the statement, which can be open statement or it can produce a closed statement. You have open statement that can produce if Boolean statement and so on. And for the closed statement, you have a simple statement, or it can produce if Boolean, closed statement, else closed statement, or closed statement can also be while Boolean closed statement, right? So as you can see, what we did, we have provided precedence by putting statement on top of the open statement, and putting open statement on top of the closed statement. So we have rewritten the production rule from this one to this one to provide precedence. So from this example, as we have seen, how does it works and how does it resolve the dangling ends? So as you can see, note that the open statement, so here the open statement have at least one if not paired with else. And if the closed statement include if statement, they must be paired with an else. So given the rules for if else, a condition statement with else can only contain another conditional in the then branch when that conditional statement comes with its own else clause. So that's how we have written these production rules. Now the only way to parse the dangling else is to associate it with the final if statement. So here, as you can see, as part of the close statement, we have mentioned that the production rule is close statement can produce if Boolean close statement, else close statement, right? So again, depending on this, we are avoiding ambiguity as well. So as I've already mentioned, note that the parse tree differs from that of the original one, because if you use the production rule from here, it will look, the parse tree will look very different if you would have used the production rule from here. Okay, now that we have looked and explored ambiguity, the next topic that we will be exploring is parse tree or concrete syntax tree and abstract syntax tree. Because remember, the main job of the parser is that it takes the input as token, it parses the token and produces the output as the parse tree. It can be either concrete syntax tree or abstract syntax tree. Either way, like the parse tree, CST or abstract syntax tree, AST, are the output of the parser. That's why it's important for us to understand the basic differences between parse tree and abstract syntax tree and what they are in general. So concrete syntax tree or CST, or also known generally as parse tree, is a tree that represents the syntactic structure of a language construct according to our grammar definition. It basically shows how your parser recognizes the language construct. In concrete parse tree, many of the punctuation tokens are redundant and convey no information, but they are useful in the input string. Now, elimination of left recursion or elimination of ambiguity involves the introduction of extra non-terminals and extra grammar production rules, as we have already noticed earlier with the example. So these details should be confined to the parsing phase only. On the other hand, we have abstract syntax tree, where an abstract syntax makes a clean interface between the parser and the later phases of a compiler. So the abstract syntax tree conveys the phrase structure of the source program with all the parsing issues resolved, but without any semantic interpretation in it. AST, or abstract syntax tree, is actually one of the intermediate representation that will be further used by the compiler, like other processes in the compiler. We can abstract away from the concrete syntax tree by deleting intermediate non-branching categories and pushing infix operator up to the nearest branching parent node. Now, if right now, after listening to this, you might still feel a bit confused, don't be, because we will take specific example and see how you can have a concrete syntax tree and convert that to abstract syntax tree. So this is an example. Let's say if you have to generate the parse tree or concrete syntax tree and abstract syntax tree for the expression 2 star 7 plus 3, then first of all, the parse tree, which is shown on the right hand side, it will look something like this, that you have the expression which is plus, it has terms or like terminals, and then you expand the terminals to factor, and you finally derive the parse tree in this manner, where as you can see, you have the tokens, which is 2 star 7 plus and 3. But along with the token, you also have other information about each token, which is 2 is a factor, or star itself is a terminal, and the terminals can also like are the 2, 7, 3, and so on, right? So here you can see the parse tree has far more information. So if we are given a parse tree like this, the way we convert that to AST is by pushing these nodes. So 2 is a node, right? We are pushing that to the nearest, so pushing the infix operator to the nearest branching parent node. What does that mean? Is that technically we are taking the 2 and we are pushing it to the operator. So we are getting rid of the factor here, or the term. And the same for 7 as well. 7, we are just getting rid of the factor and the term, and we are connecting the 7 with the operator, which is the star, directly. So the AST will look like 2 star 7 star with a plus, and plus with the 3. Now, so far, does it make sense then? Like how to convert a CST or a parse tree to an AST. Okay, thank you, Dragos, for confirming. Okay, another like example here, right? We have a concrete syntax tree, which looks something like this. You have statement can have expression, assignment, and expression. And then like the rest of the parse tree looks something like this. So the corresponding AST or abstract syntax tree, if you have to form that, what you do, you just get rid of the EXPR or ASGN and EXPR again, and you use the like node tokens itself, and you just form the relationship among each other accordingly. Now we have someone post something in the chat. Okay, Curtis has mentioned it looks like you are trimming info. Yes, that is absolutely correct. Now, theoretically, right? Theoretically, the way we produce abstract syntax tree from concrete syntax tree is technically, as we have mentioned, these are the rule, right? But in practical, what we are doing, we are technically trimming out the extra detail that are associated with the tokens. And we are just forming the relationship between the tokens, and that's how you create AST. So technically, Curtis, you are right that we are trimming information from the concrete syntax tree to form the abstract syntax tree. So now, if we have to then compare or see the differences between concrete syntax tree and abstract syntax tree, AST uses operators or operations as root and interior nodes, and it uses operands as their children. Where AST also do not use interior node to represent a grammar rule, unlike the parse tree does. AST also don't represent every detail from the real syntax tree or the concrete syntax tree. That's why they are called abstract. So no rule nodes and no parentheses are provided in the AST, for example. ASTs are also dense compared to the parse tree for the same language construct. When I say dense, it means it's more compressed, as we have all noticed from the example here, right? So the AST tree looks far more condensed or dense or compressed compared to the concrete syntax tree. So these are the basic differences between abstract syntax tree and concrete syntax tree. Now let's look into some of the implementation code that I've provided here as part of the lecture, mostly for you to have fun and to implement them and actually see in coding sense how you might be able to implement these, right? So later when I provide this as like a recorded lecture on Moodle, you can pause the video and you can use the code to see how it works in practical sense. So for example, let's say if you have the following simple language which has no left recursion. So the language is B produces epsilon, B produces BB, right? So this is an example of the language that will actually produce like the brackets. So here B stands for brackets. So this language is to produce either empty or it can produce the brackets in general, right? So given this example, notice in the following code, we separated each token in the input stream with space character to avoid tokenization. Just we will be concentrating on the parser, right? So this is the example for like a Python code that you can implement to implement the like parser for the example language or grammar that we have provided here. So at your own time, if you want to take a screenshot right now, you can do that. Or when I provide the video on Moodle, you can also pause here and try to replicate the code in Python to see how it actually works. Okay. Someone has mentioned something in the chat. So Andre has mentioned AST is basically needed to plan and simplify language hierarchy for parser development. No, actually, again, so remember compiler, right, has like in general or traditionally compiler has two parts, front end, back end. Now front end has several parts. The back end has several parts, right? The main parts of the front end is, let's say, lexical analysis or done by Lexer, where it takes the input string of the program or the language that you have defined. The lexical analysis then produces a token. The token is then being processed by the parser or the parsing analysis, which then produces the concrete syntax tree. Now, concrete syntax tree is technically, it is the hierarchy for parser development. So it creates the hierarchy between the token based on the input string. And then based on that concrete syntax tree, we form the AST by deleting or like taking out information that are not required. The reason we produce the AST is because AST acts as an intermediate representation. Now, why intermediate representation is important is because intermediate representation then moves to the optimization phase, which is part of the back end of compiler. And then intermediate representation will be further optimized to produce optimized intermediate representation code. And then from the optimized intermediate representation code, you will generate specific, like hardware specific or system specific executable file. And then the executable file will be linked with other libraries and like packages that your hardware might require. And then the executable will be executed on the specific hardware or system to finally get the output. So that's the whole process of the compilation or compiler. So AST is one of the, let's say, intermediate representation form, which is generated as part of the parsing or by the parser, so that it can be further processed by the back end of the compiler. Okay, amazing module finish. Well, technically, yes, module finish, but again, we still have to do deep dive into each of the other phases that are remaining. So right now we have reached till the AST, which is the middle point of the whole compiler, right? Because AST is the intermediate code representation. But the intermediate code will be further processed to do optimization, right? Which will be part of the backend of compiler. And we will explore these in the next lectures. Okay, so again, on your own time, you can try out this code and see how it works for you. This is another example that I have provided. This is for expression language, right? This is an example of the production rule for grammar for expressions, to analyze expressions. So the code is provided here. Again, when I provide the video on Moodle, you can pause and you can try the code out in Python to see how it actually works, right? This is the continuation of the this example that I have provided for expression language. So also, these codes are also available in the lecture slide. So if you want to download now and try it out on your own, please be my guest, go ahead and do that. Okay, now that being said, we have reached the end of today's lecture. Now let me stop sharing and let me pause the recording.